Okay, so this is problem 33 of chapter 8, and it's a response video for one subscriber, but it also answers a question for a second subscriber. So this person didn't request anything other than for me to solve this, but I got a question from two subscribers about the dx dt. What does it mean? How do you find it? And so I will address those questions in this problem because this problem, the dx dt, is a little bit tricky. So the steps for solving all step equations are pretty much the same. First, you have to find initial conditions, and you have to find final conditions for the x, whatever it is that you're looking for. The second thing you have to do is find the damping, because the damping will tell you what sets of equations you'll use to find the coefficients for the general equation. The third step is you have to then solve for the coefficients of the general equations. And a critical skill in knowing how to do that is understanding dx dt, what it is, and how to find it. And ultimately, dx dt is driven by what is it that you as an engineer are looking for. Are you looking for current, the general equation for current, through a capacitor, through an inductor, or are you looking for voltage through a capacitor? So what are you looking for? That will drive what the dx dt is and what initial conditions that you're looking for. So we'll go through all of that, and this is a great problem because the dx dt isn't something trivial like 0. It's actually something, so we'll find that. So in this problem we have a 240 volt source connected to a 5K resistor, another 5K resistor in parallel with a 5 microfarad capacitor, and you have a switch. Switch 1 is open at time 0. You have an inductor, and you have switch 2, which is closed at time 0 but opens. We have a 1K resistor and a 60 milliamp current source. So at time 0, you have this one closing while this one opens. They're synchronized. So we have to take a look at what it looks like, the circuit looks like before that switch the switching occurs, and we're looking for the general equation that will describe current through the inductor. So that's our goal. So the first thing we have to do is find initial and final conditions. Let's take a look at the circuit before the switch closes. We have this open and this closed. So this part of the circuit, since there is no connection to it, goes away, and all we have is from here to here. And we have an inductor that is a short. We've got this closed. The inductor is going to short out this 1K resistor, and so what we're going to have is this 60 milliamp source which is going in a loop like that. So the IL is in the direction of the current source, so the current will be positive. We know that's going to be I0. IL of 0 then is equal to 60 milliamp. Park that value over there. Now let's take a look at what happens after the switching happens. We got this closing and this opening. So right now we've got something that looks like this. What's that at infinity? That is what the final conditions are. Well, as time goes on, this is going to be a short. Capacitor is an open. Capacitor is an open. This is going to be, we're looking at final current, so we need to do a source transformation of this into a current. So we source transform that, gives us, so 240 over 5 K. Gives us 48 milliamps. Got two resistors. Now, actually, it doesn't even matter. I could go through and simplify that into one resistor, which we will do. If you have two of the same value, then the equivalent resistance will be half of that. So it would be 2,500, but it doesn't matter because the inductors are short, and so this is going to go in this loop like that for your I final. So I final going to be 48 milliamps. Those values we need. Now we need to take a look at damping, and that requires just looking at alpha and omega. So what's alpha? 1 over 2RC. Omega naught is 1 over root LC. This is 1 over 2. The damping, notice we have a 1K resistor here, and then we have resistors here. So what is the R that we're talking about? It's not, the R, the alpha and omega naught are constants that are relevant only after the switching, after time 0, because they tell you about the damping effect. So anything before time 0 becomes irrelevant. We don't care about that. So we're looking at this one. And this, once we source transform, is really this in parallel with that, right? So once we source transform, what we really have is 48 milliamps like that. 5K here, 5K here. And that's really the same thing as 48 in parallel with 25. And so 2,500, and that's where that 2,500 comes from. So that's going to be 2,500 times our C is microfarads. So let's enter that. 500 times 5. We get a value here of 40. Over here, we have 1 over root. Oops, this should be 80 and loose. Yeah. Root 80 times 5. And that gives us okay, that gives us a value of 50. So we have a situation where omega naught is greater than alpha, therefore this is going to be an underdamped response. So then we look in our book for the equations for an underdamped response. And these are the 3 equations that we are going to be working with. And instead of dx dt, I'm just going to actually write down what it is we're looking for. The x is just a general variable placeholder for the engineer to plug in. Okay, this is going to be dc dt, dv dt, di dt, dc dt. What is it? So that's what's really super cool about this, is that you have a general equation that describes it for everything. And you just have to know what you're looking for and what the initial conditions are. So for the underdamped, the equations are, we're looking for di dt, and we're looking for, this is the final equation, IL of t will be I final plus B1 prime cosine omega d t plus, I'm going to move these two up here, IL0 need them. I, L, 48 milliamps. U. We need those for our general equation. So omega dt plus B2 prime omega d t e to the minus alpha t. Okay, so right away we have this piece of the information. We calculated alpha to find the damping, and alpha was 40. So that part is done. Is there anything else we need? We need omega d. So omega d is the square root of omega naught squared minus alpha squared. So that is going to be omega naught was 50, 50 squared minus 40 squared. And put that in your calculator. Square root of 50 squared minus 40. Now that gives you 30. So let's replace omega naught here with 30. 30t, 30t. Okay. And what else do we have? We have the final. This is going to be 48. And we have everything in terms of milliamps. So now we've done 90% of everything of the equation. We need to find B1 and B2. And to find B1 and B2, we have two unknowns. We need two equations. The two equations are, that we have are going to be IL of 0 is equal to I final. And I'm going to use my notation so that I don't confuse you. But when I do the problems, what they have as final, my equivalent is IL of infinity. And if that confuses you, let me know. I can stop doing it. But I like to use infinity because you understand what infinity is, and I just have a habit of doing it. So so I always revert back to it. So we have IL of 0, IL of infinity, plus B1 prime. Well, that's equation number 1, and fortunately for us, we actually have everything we need to solve this equation. We solved for, that's step number 1, was we found the current at times before the switching, and the current after the switching happens for a long time. What is our initial current? We have 60 milliamps. That's equal to current of infinity at time infinity, 48 milliamps. That's going to give us our coefficient B1 prime. So plus, bring that over here, gives us 12 milliamps. It's equal to B1 prime. So all that's left now is B2. What is our equation for B2? Our coefficient equation, our other coefficient equation is DIL of 0 plus dt is equal to negative alpha B1 prime plus omega d B2 prime. We know a lot of this information. Negative alpha. Alpha was 40. Omega d is 30. And B1 prime we just found to be 12. So 12 times 40, 40 times 12, this is negative 480. And the trick now is DIL dt at time 0. Well, what is that? That is current through the inductor right after the switching happens. Be very careful when you see DIL dt or dV, d. When you see current through the inductor it's pretty possible to say, well, current can't change instantaneously through an inductor, so this has to be 0. So then you set this equation to 0. The reason why that's wrong is because it's true that current can't change instantaneously, but it can change voltage instantaneously. And the same vice versa. You have voltage, dVc of the capacitor. You have to look at the fact that the capacitor can't change voltage instantaneously, but it can change current instantaneously. So if you're looking at the inductor, you have to look at the inductor equations from, I don't remember what chapter it is, but we're solving for inductor currents, so the dx dt, what is that? That's going to come from the set of equations for the inductor. So step 1, number 1, ask yourself, what am I talking about? Am I talking about a capacitor, or am I talking about the inductor? If you're talking about the capacitor and you're looking at current equations from the inductor, that's wrong. If you're talking about an inductor, you're looking for equations in the capacitor section, that's also wrong. So in this case, step 1 is to ask yourself, what am I looking for? In this case, this dx dt is the di, or in this case, this di dt is not dic sub c dt, this is dil dt. So look at your equations for the inductor, and you'll find that there is an equation that says VDIL dt let's see, what was that? No. V is equal to L di. Okay. So in this case, the dx dt is di dt. In the case of capacitor voltage, the dx dt would be dv dt. So now we can solve for di dt by saying that di dt is equal to v over L. Well, what is v? What is v? What is L? Well, we're looking for actually dil dt 0 plus, so this has to be voltage at times 0. And the inductor is just a constant of 80. So what is the voltage across the inductor at time 0? Find that, and we have di dt. So to find that, we have to, I'm going to park this over here. di of 0 dt is equal to v, the voltage change right after the switching happens, over inductance. Okay, right after the switching happens, what do we have? We're looking for voltage, so we don't, doing a source transformation is not going to help us. But right after the switching opens, what we really have is, we have this, this voltage, 240, right? I don't need this anymore, so I'm actually going to get rid of this. This is what our circuit looks like immediately after switching. We have the capacitor right now, or think about the time before switching. What's happening? The capacitor is open. It's getting charged up by this 240 volt. But what charge does it have? Well, the charge that it has is, you can do voltage division over here because it's in parallel with this resistor. So if you do voltage division, then we have the capacitor charge is charged up to 240 volts times 5 over 5 plus 5. And they're equivalent resistances, so it's just going to divide it in half. So the capacitor, right before the switching happens, has a charge of 120 volts, right? So why do we care? We care because the capacitor is in parallel with the inductor, so the voltage across the inductor must be equal to the voltage across the capacitor right after the switch closes, because the inductor can and does change voltage instantaneously very fast. So right after the switching happens, this is 80 or 120 volts, and this is 80 henries. So 120 over 80. That gives us 1.5 amps. We have everything in terms of milliamps, so now we know what DIDT is. DIDT is 1500 milliamps. Now we can go ahead and solve for B2, and that's just algebra. So we go 1500 plus 480 divided by 30. We have B2 prime is equal to 66. And that was the last thing that we were looking for. So your general equation for the general equation for the circuit that we had originally is IL of t is equal to 48 plus 12 cosine 30t plus 66 30 sine t. Sine 30t, I lost my sign, times e to the negative 40, 40t milliamps. If you're on a test, you may want to take a second just to make sure that this equation makes sense, just by checking the initial and last final conditions. At time 0, cosine is 1, sine is 0, this goes away, and this is 1. So we have 48 plus 12, and that gives us 60 milliamps, which agrees with what we said it should give us. So at time infinity, a negative exponent goes to 0. So this whole term goes to 0, and we have 48 milliamps, which agrees with what we said, just looking at the circuit, doing circuit analysis, without using any math at all. It agrees with what we said that the final current should be. I hope you found this helpful, or at least not more confusing. Thanks for sending me the request. Have a great day.